Today in this lesson, we're going to be talking about reaction types and specifically how to predict the products of a reaction when you only know what the reactants are. Okay, so if you only have stuff on the left side of the reaction equation and nothing on the right side. This kind of gets at like the most important aspect of science in general, which is if I do this, what's going to happen. Okay, so that's like probably the most important thing that we get out of science is being able to predict what's going to happen. And in chemistry, right, we want to know if I mix these two chemicals, what am I going to produce? What am I going to form? So is it going to be this compound or that compound? Is it going to explode? These are the questions we want to be asking before we do a reaction. So there's basically three steps, to predicting the products of a reaction and making sure it's a complete reaction equation. The first is to identify the reaction type. And the second is to then predict the products based off of what we know about that reaction type. And the last step is always going to be to balance the equation, right? We can't leave any reactions unbalanced because that violates the law of conservation of mass, and a whole bunch of scientists would be upset at us if we did that. Let's start with a synthesis or a combination reaction. So I'm telling you that this is a synthesis or a combination reaction, but you should also be able to identify it because we have two elements that are reacting. If I have two elements reacting, what they're going to form is a product where both of those things are in a compound. So the generic equation for a synthesis reaction is A plus B, where A and B are elements, combining to form some compound between the two. Now, since magnesium is a main group metal and nitrogen is a nonmetal, we know that this is going to form an ionic compound. And actually, we know a bit more, right? We know that magnesium, if it's going to form an ion, is going to be a 2+ ion. And nitrogen, and if you don't believe me, look at the periodic table, look this up. Nitrogen, if it forms an ion, is going to form a 3- ion. So with that information, the ionic compound that this is going to form has to have a certain formula. So we need the ionic compound to have a net zero charge. Since these aren't, since this one's 2, this one's 3, we can't just change one of these. We have to change the amount of both of them. So if we have 3 magnesiums, that gives us a 6+ charge overall. 2 nitrogens gives us 6-. So that's going to be the formula for our product here. We're not always going to be able to predict what the state of the products are, but oftentimes we will be able to. In this case, it's going to be a solid because it's an ionic compound. Remember, ionic compounds have really high melting points, so it's going to be a solid unless we're running this reaction at like 7 million degrees Celsius, right? Not really that high, but thousands of degrees Celsius. A few things. So like I said, we're only going to be able to predict the products of a synthesis reaction if we have two elements combining to form an ionic compound. Okay, so we're going to limit what we're going to be expected to know in terms of what synthesis reactions we can predict the products for, based off of that criterion, one of the two. And we're also only going to do synthesis reactions where we have a main group metal reacting with a nonmetal to form an ionic compound. If it were a transition metal like iron forms multiple charges, and that's going to make it really difficult to predict the products. If magnesium, instead of magnesium, if we had something like iron forms a 2+ or a 3+ charge. So we wouldn't really be able to predict what the product would be in that case. Last step is always going to be to balance the equation. So I've determined in the second step, right, predicting my products, I've determined what the formulas and these subscripts are of my products. In the last step, now I'm done messing around with the subscripts. In the last step, when I balance the equation, that's where I'm only changing the coefficients of the reactants and products. So if I look over here, right, I've got 3 magnesiums and 2 nitrogens. Here I have 2 nitrogens. I need 3 magnesiums on this side, so I put a 3 here, okay? Next type of reaction, decomposition. So A decomposition reaction is always when I have one thing breaking up into many things. Okay, and just like with a synthesis reaction, I could have two things reacting to form one compound. I could have three. I could have five. With a decomposition, we usually write it as just one thing breaking up into two. But I could also have written this as ABC goes to A plus B plus C, right? So it could have many products. I'm only going to be able to predict the products of a decomposition reaction in one specific case when the reactants are decomposing into its constituent elements. So remember, the term constituent means to make up, right? Or what makes up something, or a smaller piece of a bigger whole. So here, the constituent elements of iron oxide, iron 3 oxide, are going to be iron and oxygen. So the first thing we need to identify are what are those elemental forms of those elements. So here we've got iron. Iron is an element, and this is true of all metals. Basically, all the elements except for those diatomic gases or diatomic molecules that we talked about, diatomic elements, excuse me. All the other ones are just going to be the element. So iron is just Fe, right? We don't have to add any subscripts or anything like that. Oxygen, we talked about, is one of those diatomic elements. So oxygen occurs as O2, and we know it's also a gas. So the products here are just going to be those elements, right? So I don't have to worry too much about this, right? All I have to do is take the elements that are here, write them individually on the product side, and just make sure that I have them in the correct form. Again, I'm only going to ask you to predict the products for decomposition reactions when it's going from a compound to its constituent elements. So this is actually, if I take rust and heat it up hot enough, this actually does happen. So rust is the kind of stable form of iron and oxygen at room temperature. But if I heat it up hot enough, this will end up producing, actually it would be liquid iron in this case, because it'd be a really high temperature. But it would form just iron and oxygen gas would be released. So here I have the balanced chemical equation, right? After I've predicted what the products are, then I can go in and start messing around with the coefficients. Here I've got a single replacement reaction, right? So the generic equation is when I have an element reacting with a compound. And there's two ways this could go. This element could either replace the cation in my compound, or the element could replace the anion, right? Either one of the two will get replaced by the element that's on its own. So in this case, we have a metal reacting with an ionic compound, and so the metal is going to replace the other metal in the cation. So we're dealing with this equation here, actually. So A plus BC, A is going to replace B, which is the cation here, to produce AC and B. So we're going to end up with iron as on its own here, and calcium is now going to ionically bond with nitrate. So we need to know what the formula is for calcium. Calcium is a metal, so basically it's just saying that we're using this generic equation. And we need to know what the elemental form of iron is and the charge that calcium takes, right? Because if calcium is going to be in an ionic bond, we need to know what charge it's going to have. So iron, like we said, is just going to be Fe. All right, so that one's easy. Calcium, we also know, is a main group metal, always forms a 2+ charge. So since nitrate is what's left, the anion, and nitrate has a -1 charge and calcium has a 2+ charge, the product there is going to be calcium bonded to 2 nitrates. Okay, so there are 2 products, iron and calcium nitrate. So again, now the last step, now that we've made our products, we've determined what these formulas and subscripts are going to be, the last step is to add in those coefficients and balance it here. So I could go through the steps of how I balance this, but we already had a whole lesson on that. I figure you guys will be able to do it. All right, so the other type of single replacement reaction is if I have a nonmetal here. Okay, so a nonmetal is not going to replace the metal in this case. The nonmetal is going to replace the anion, which is typically going to be the other nonmetal. So the generic equation I'm working with is this one here. So A plus BC is going, so A is going to replace the anion here, C. So I'm going to end up with Ba, right? So my cation and my new element, and C is going to be left on its own. So again, I need to know what is the, so here's the rationale again. Fluorine's a non-metal, so it's going to replace chlorine. So I need to know what the elemental form of chlorine is, since chlorine is going to be left on its own, and we know actually chlorine is in one of those diatomic gases. And iron, we still know, is the same. Iron is now the cation. That's not going to change. But fluorine, we need to know what charge fluorine is going to take as an ion, and we know that fluorine takes a 1- charge. So what we're going to end up over here with is chlorine gas, so Cl2, and it's going to be iron, and iron's not changing its charge. It's still going to be 3+, so it's going to be iron with 3 fluorines bonded to it, or fluorides. Okay, so here are our products. We predicted our products. Last step is going to be to balance it. Okay, there's our balanced chemical equation. We've completed that reaction equation. Here's a video of a lemur. Yep, that's freaky. All right, so redox reaction, combustion. These ones are really easy to spot. I'll usually have something like a hydrocarbon, so a compound that just has carbon and hydrogen, or I'll have something that has like carbon, hydrogen, and maybe some oxygen bonded in there too. And it'll be reacting with just oxygen, right? So actually, if I look at this, hi there again, lemur. If I look at one of these reactions back here, so, oh no, I thought I had it here. Never mind. Some of these, I could also have a combustion reaction that does not have a compound like this, right? If I had like calcium reacting with oxygen, that would be both a synthesis and a combustion reaction, but it's more easily predicted as treating that as a synthesis reaction. So the reactions that we're going to treat as what we will call a combustion reaction here are the ones where we have compounds with carbon, hydrogen, and possibly oxygen reacting with oxygen gas. Okay, they have this general equation, right? Compound with carbon, hydrogen, oxygen reacting with O2, and it's always going to form CO2 and H2O in these cases. So we just plug in CO2 and H2O, right? Really easy predicting products here. You'll only be asked to predict combustion reactions for these kinds of compounds reacting with oxygen. Always CO2 and H2O, and then you just have to go through and balance it. Precipitation reactions are easy to identify because we'll have 2 ionic compounds here. Or we potentially could have an acid or a base, but typically those will produce ions as well, and so we end up having a precipitation reaction be possible. But I'll talk about that a little more when I talk about acid-base neutralization reactions. So if I have 2 ionic compounds, immediately I know this is a precipitation reaction. It's going to have this general formula. AB plus CD goes to AD and CB. So A is now going to bond with D, and C is going to bond with B. So in this case, what we've got is barium bonding to phosphate. This is this would be D, I guess, in this case. And K is going to bond to Br. So we have 2 aqueous ionic compounds reacting. We need to figure out what those charges are on those ions so that when we swap the partners, we can predict what the formulas of the products are going to be. So barium has a 2+ charge, phosphate has a 3- charge, so we're going to need barium 3, PO4 2, right? 2 phosphates giving us 6-, and 3 bariums will give us 6+. In the case of potassium and bromide, potassium is 1+, bromide is 1-, so we will have a 1-to-1 ratio. So the products are just going to be based off of those charges, and this is what it's going to look like. 3 bariums to 2 phosphates, and 1 potassium to 1 bromide. Okay, again, now I've predicted the products. I'm going to leave the subscripts alone, and now I'm going to go through and put in my coefficients. Okay, and if I do that, I get that. Okay? Acid-base neutralization reactions. Like I was saying, sometimes you can get precipitation reactions that have acids involved because acids split up into ions. Sometimes I can have acid-base neutralization reactions. Sometimes I can have precipitation reactions that involve sodium hydroxide because this actually, even though it's a base, it's also a ionic compound, right? Sodium's a metal, hydroxide's a polyatomic anion. But in order for it to be an acid-base neutralization reaction, I have to have both an acid and a base. So if I'm missing one of these, it's not an acid-base neutralization reaction. Okay, I need to have here's my generic acid and some base. In this case, we're always talking about the base being hydroxide. Okay, the products are always going to form H2O, right? So the hydrogen here on my acid is going to combine with the hydroxide to form H2O. And what's left, those ions that are remaining, are going to form some kind of salt. Okay, so in this case, I've got a diprotic acid, right? So H2SO4, sulfuric acid, has 2 acidic hydrogens. Hydroxide can only pick up 1 hydrogen each per hydroxide, so I'm going to end up needing more than just 1 equivalent of sodium hydroxide. So if I end up combining hydroxide with the acid, what's left is sodium and sulfate that are going to combine. So sodium's 1 plus, sulfate's 2 minus. I end up getting Na2SO4. There are my products, right? Here's my water, and here's my salt. So now that I've completed that, I need to put in my coefficients, right? I need to balance this equation. Since I have 2 sodiums here, I can see I'm going to need 2 sodiums over here. And like we said, since I have 2 acidic hydrogens, I'm going to need 2 hydroxides. So that works out, right? So 2 hydroxides here, and actually what that's going to lead to is needing 2 waters as well. Okay? So just to recap, 3 steps that we have to complete a reaction equation. So if we're given a reaction equation that just has reactants, we want to end up with a full, complete, balanced equation. This is what we have to do. First, identify the reaction type, right? And that's based off of what the generic equations look like for each of these 6 reaction types that we have. We need to predict the products, okay? And this is where I'm going to determine what the subscripts are, or the formulas, right? The chemical formulas for each of my products. Once I'm done doing that, I will need to leave the subscripts alone and balance the equation. So that's where I'm going to go in and change the coefficients. So I don't want to, a common mistake students make is to mix up these 2 steps. So if I put in once I predict the products and I put in my subscripts and I go to balance it, I can't change those subscripts, right? Because that would mean that I'm making something else. And I've already determined in step 2 what I'm making. Okay, so you just need to make sure that you're clearly separating all 3 of these steps. So let's take some examples here. So let's say I've got calcium, so solid calcium and oxygen. So again, this could be a combustion reaction, right? Because we have something reacting with oxygen. But when I'm predicting products, this is going to be more easily completed if I look at this as a synthesis reaction, right? I have 2 elements combining, and that's going to form products here. And the product is going to be an ionic compound. Calcium's a metal, oxygen's a nonmetal. Calcium forms a 2 plus charge when it's an ion. Oxygen forms a 2 minus charge. So it's going to be a 1-to-1 ratio, calcium 2 plus, oxygen 2 minus. And the last step here, right, I know it's going to be a solid as well because it's an ionic compound. The last step here is going to be to balance the equation. Throw in some coefficients here to make sure I have the same number of atoms on both sides of the reaction equation, of the reaction arrow, I guess. Here's another one, super easy to identify. So again, I've got oxygen by itself, but here I've got a hydrocarbon, right? A compound that just has carbon and hydrogen. When carbon and hydrogen combine with oxygen, it's a combustion reaction. Oops, somehow we got backwards, okay. It's a combustion reaction, and the products are always going to be CO2 and H2O. Always, always, always. Okay, super easy to identify the products. Once I know that, I just have to go in and balance the equation. Boom, done. Next. All right, magnesium combining with silver nitrate. Magnesium is a solid, it's an element by itself, and here we've got silver nitrate, which is a compound. Magnesium's a metal, and here we have silver, which is a metal, and nitrate, which is a polyatomic ion made up of nonmetals. So this is going to be a single replacement reaction because I have a single element reacting with a compound. Again, since magnesium is a metal, it's going to replace the metal in this compound, or the positively charged thing. So magnesium is going to replace silver to form magnesium nitrate, and silver is going to stay by itself. Now we knew this is going to be MgNO3 because magnesium forms a 2+ ion when it forms an ion, and nitrate's not changing its charge. So I need 2 of these nitrates because they have -1 charges, 2 -1 charges to balance out magnesium's 2+ charge. Now I just go in, balance the equation, right? I've got 2 nitrates here, 2 nitrates here. I'm going to need 2 silvers, which means I'm going to need 2 silvers here. And that's it. All right, so that's the end. You'll have some practice problems after this, as always, and I hope this video was helpful. Let me know if you guys have feedback.